Welcome, everyone. Good morning. Welcome to the third day of activities of the second CompChem, and I'm glad to be the chair of this morning again. My name is Rodolfo Fiorotti, and I am professor of the Organic Chemistry Department of the Universidade Federal Fluminense. I would like to start by thanking everyone's presence today, the audience, especially the oral lecturers. And this morning, we are having a round of 3 oral lectures from invited researchers that are members of the project Sprint. Thus, I would like to enjoy this moment to give a thank to the funding agency, CAPES, and the program Print that made possible make this event free for all of you. The speakers will have a round of 20 minutes to give their lectures, and we'll have a round of 10 minutes in which we can will answer the audience's questions. So please feel free to ask in the chat during their talks, and we'll try to answer as many questions as we can. Our first lecturer today is PhD Ana Carolina de Albuquerque from Universidade Federal Fluminense. She is a postdoctoral researcher of LAMEC UF, a lab in the UF, and she will give a talk about applications of NMR chemical shift calculations in the structural elucidation of natural products. Thank you again for accepting our invitation, and you may start whenever you're ready.
Okay, thank you, Professor Rodolfo. Good morning, everyone. My name is Ana Carolina Ferreira de Albuquerque. I'm a postdoctoral researcher at the Chemistry Institute of Fluminense Federal University, and I'm here today to talk a little about applications of NMR chemical shifts calculations in the structural elucidation of natural products. And before we talk about NMR calculations, we should discuss a little bit about natural products. Natural products are substances produced by secondary metabolism of plants, fungi, and bacteria. Usually, natural products play important physiological roles in the interaction of the organisms that produce them with the environment. And some examples of these important physiological roles are defense against pathogens, protection against abiotic stress, and attraction of pollinators. It's very common that natural products display biological and pharmacological activities, and such activities depend directly on their chemical structures. Therefore, it's crucial to have a correct structure and reactivity relationship. So, it's necessary a correct structural elucidation of natural products. Until half of the 20th century, the structural characterization of natural products was mainly based on chemical synthesis, and it was done degradation and derivatization reactions. But this kind of strategy had some limitations, like usually the work took years to be completed, usually large amounts of the substance were required, and usually, in many cases, the assignment of relative and absolute configurations wasn't possible. But from the 60s until nowadays, the chemical synthesis was replaced by spectroscopy methods, especially nuclear magnetic resonance spectroscopy, mass spectrometry, and circular dichroism. And this type of methods has some advantages, like the structures of complex molecules can be elucidated in much less time than before. Usually, only few quantities of the material are required, and usually the sample is not degraded. In the last few decades, nuclear magnetic resonance, NMR, became one of the most widely used methods for the identification and characterization of natural products. And it was mainly due to the developments in new technologies in this kind of method. Two recent advances in this method that allowed this method to become one of the most widely used was the development of more sensitive spectrometers, and the advances in multidimensional spectra. But even with such developments, the structural elucidation of natural products with complex and rare skeletons remains a challenging task. And this happens because significant changes in the molecular structure might generate only small changes in NMR spectrum. Therefore, it's very common to see in the literature many revisions of erroneously established structures for natural products. In the last decades, calculations of NMR parameters became powerful and inexpensive tool that can complement experimental NMR data in the characterization and determination of natural product structures. And there are two main classes of primary NMR data that can be calculated by quantum mechanical methods, such as chemical shifts and Copley constants. But between those two, the chemical shifts are the most important one for the diagnosis of the chemical and magnetic environment of the nuclei. In the last decades, there was an increased interest in predicting NMR chemical shifts through quantum mechanical methods such as ab initio and DFT level of theory. And this happened because of the recent developments in both quantum methods and hardware, which made this type of calculations more accessible and more accurate. And this kind of calculations have several applications to natural product structures. And the main applications are the assistance in assigning spectra, and it's possible because there's a clear correspondence between the calculated chemical shifts and the nuclei that generated the calculated chemical shifts. And also, the most important one is the elucidation and revision of chemical structures. So in the literature, it's very easy to find several applications of this kind of calculations in natural product structures. And usually these kind of calculations follow a basic procedure that is composed by few steps. The first step is the construction of the three-dimensional structure for every candidate structure of that natural product. And then for each candidate structure, they are submitted to a conformational analysis procedure to obtain all the relevant conformers for the natural product. Then each conformer is submitted to a geometry optimization step, and then there is a energy cut based on a Boltzmann distribution procedure. And then the selected structures are then submitted to chemical shifts calculations. And if you are doing a calculation for a natural product structure, usually this means calculations of carbon-13 and proton nuclei. And once you have the calculated chemical shifts, you can compare them with experimental data. And then you can quantify this comparison by the use of statistical tools, and then determine which candidate structure better correlates with your experimental data. Like I said before, the first step in the procedure is to construct the three-dimensional structure of each candidate structure of the natural product. And this step can be done in several softwares like Argus Lab, Avogadro, ChemSketch, ChemDraw, HyperCam, and GaussView. The second step is a conformational analysis. So each candidate structure is submitted to a conformational analysis procedure, and it can be done in two main ways. If you have a molecule with few rotatable bonds, you can perform this conformational analysis by doing a systematic conformational search, where you can vary the bond angles and bond lengths in a systematic and predictable manner. But if you have a complex molecule with several rotatable bonds, which is very common in natural product chemistry, you can perform a randomized conformational search, where the bond angles and bond lengths, they are varied in a randomized manner. Usually, works published in the literature use the Monte Carlo algorithm along with force fields like MMFF or MM+, in softwares like Spartan, HyperCam, Micromodel, or Conflex. In this step, conformers with relative energy within 5 to 10 kilocalories per mole are selected for the subsequent steps. All the selected conformers are submitted to a geometry optimization calculation done in Hartree-Fock or DFT level theory in softwares like Gaussian, GAMES, or Orca. It's important to highlight that it's highly recommended that once you do a geometry optimization, you also perform a calculation of normal modes of vibration to confirm the structures as energy minima at the potential energy surface. And these calculations of normal modes of vibration usually are done in the same level of theory as the ones used in the geometry optimization step. After this, there is a new energy cut based on a Boltzmann distribution, and conformers with relative energy within 2 to 3 kilocalories per mole are selected. And these selected conformers are submitted to chemical shifts calculations. And as I said before, when we are doing these calculations for natural product structures, usually we perform these calculations for carbon-13 and proton chemical shifts. Usually, we use GL method along with DFT level of theory in softwares like Gaussian, GAMES, and Orca. There are several density functionals that in the literature are used for this kind of calculations, and the most used are B3LEAP, MEP W1 PW91, PPE0, and 062X, WC04, and WP04. And it's important to emphasize that when you do these calculations, the parameter that you get at the end of calculation is not the chemical shift itself, but is a magnetic shielding tensor. And you can convert this tensor in a chemical shift by the use of internal standard. And when you are doing these calculations for natural product structure, usually this internal standard is the TMS. Then once you get the calculated chemical shift, you can compare them with experimental data. But this comparison you can do directly with the chemical shift itself, or you can do it with scaled chemical shift by applying linear scaling factors. Linear scaling factors are methods for reduction of systematic errors by applying a linear equation to the calculated chemical shifts in order to transform them into scaled chemical shifts. And this method is capable to cancellate errors arising for several sources, like the negligence of solvation effects, negligence of reverberation effects, and so on. And to quantify this comparison between calculated and experimental chemical shifts, you can use statistical tools. So by the use of statistical tools, you can also determine which candidate structure better correlates with the experimental data. You can use classical statistical parameters like mean absolute deviation, root mean square deviation, and R-square, or you can use more modern statistical tools like DP4, DP4 plus, or JDP4. And there are much more statistical tools available nowadays in the literature, but these three are the most widely used. And these type of statistical tools can classify each candidate structure based on the difference between calculated and experimental data using a statistical procedure based on the student's t-test. So to show you some kind of work we do in our research group, I brought to you a published paper, a very recent published paper called Unraveling the Alien Family, a Complementary Quantum Mechanical Study. In this paper published last year, we applied calculations of chemical shifts in order to elucidate the structure of a natural product. In 1993, the natural product called Alien A was isolated from a marine sponge from the species called Elianthus annus. 4 years later, a new natural product was isolated from another marine sponge in another species called Aliclona fascigera. Based on the comparison of NMR spectra between those two natural products, the authors then determined that the structure of this new natural product was very similar with the structure of Alien A. So they call this new natural product Alien A. And then both biosynthetic routes for these natural products were proposed. And then the authors proposed that the structure of the Alien A came from another natural product called curcuphenol. Prates and collaborators in 2011 proposed a synthetic route for the structure of Alien A based on the biosynthetic conversion of curcuphenol to the Alien A structure. Nevertheless, the NMR data for the synthetic and isolated products didn't match. So the authors proposed that the correct structure for this natural product was similar to curcuphenol without the 8-member ring proposed at the Alien A structure. So this new structure was called curcudiol. So in order to elucidate the correct structure of this natural product, and keeping in mind that the reisolation of the original natural product was very difficult, we performed the carbon-13 chemical shifts calculations using GL-DFT level of theory. We simulated both chemical shifts for Alien A and curcudiol structures, and then compared them to experimental data. So in this first graph on the left, we can see that for Alien A structure, the carbon atoms that are supposedly related to the cyclization reaction from curcuphenol to Alien A, carbon atoms 1, 2, 6, and 8, display the highest deviations from the experimental data. At the same time, the carbon atoms from the curcudiol structure show very little difference between calculated and experimental chemical shifts. We also applied the DP4 plus procedure that indicated that with almost 100% probability that the calculated data for curcudiol structure was correlated to the experimental data. So these results strongly indicated that the correct structure for this natural product was actually curcudiol, as was proposed by Peto's group. In summary, the correct structure determination of natural products is crucial for the study of their biological and pharmacological activities. And many natural products have complex and rare skeletons, and their structure elucidation is a challenging task. In this scenario, quantum mechanical calculations of spectral properties, especially carbon-13 and proton NMR chemical shifts, can be a powerful and an expensive tool in the assistance of structural determination. In the literature, it has been seen even more recent developments of calculation protocols and its applications in complex natural products. So to finish this presentation, I would first like to thank CAPES for the funding of my scholarship. I would also like to thank my post-graduation program at the Chemistry Institute of UF, and also like to thank LAMEC, my research group, and thank you for your attention. And if you have any interest to know more about quantum chemical calculations of NMR parameters and its applications in natural product structures, please check our recently published review paper at Organic Chemistry Frontiers. Thank you very much.
Thank you. Thank you so much, Ana Carolina, for your brilliant and clear explanation. There was very much like a tutorial in which we could learn and gather some hints of how we can use strategically the computational tools to solve natural products problems. That was very nice. We have some time here to answer the questions. Uh, Professor Luciano Costa asked here in the chat, could you comment a bit about the care with the level of theory for NMR calculations?
Okay, yeah. Usually, when we do this kind of calculations, we use DFT level of theory. They usually give the more accurate results along with low computational cost. So usually we do these calculations using DFT, mainly because natural products are complex structures. So if we do this kind of calculations with Hartree-Fock or molecular mechanics, we usually don't have much accurate results. And if we do with DFT level of theory, we can have good results. And in the literature, there are several benchmarking studies with researchers evaluating several different density functions for several types of systems, of types of molecules in natural products. So in this kind of benchmarking studies, we can choose the best density functional for our type of molecule. And it's important to highlight that we also have, especially for chemical shifts calculations, we also have two density functionals that were parameterized and created especially for this kind of calculations. And I also cited them on this slide. It was WC04, which was created for carbon 13 chemical shifts calculations, and WP04, which was parameterized and created especially for proton NMR calculations, chemical shifts calculations. So these two density functions, they usually give really good results for this kind of calculations.
All right. I believe that was a very thorough answer, very explanative. Toyes Uyegoki from France, I believe he said, or she, I don't know, asked if you could later to share the review here in the chat after your presentation.
Of
Okay,
course, yeah,
but
of course.
I believe Toyes could take the reference from the screen right now.
Yeah, but I can send the link, no problem.
All right. Professor Fernando Martins also asked here, can you tell us about how solvent effects can be used in this kind of NMR simulations?
Oh yeah, because of the time problem, I didn't have much time to talk about solvation effects. But there are two main types of two manners of to deal with solvation effects in this kind of calculations. You can do it explicitly or implicitly. Usually, when we do these calculations with natural product structures, we get good results by doing with implicit solvation. It also has advantages because implicit solvation requires a low computational cost. So, but we usually do with implicit solvation like PCM, and usually we don't require explicit solvation because the type of solvent that are used in NMR experiments, they are like more apolar and aprotic solvents. So they don't have like a specific type of interaction with the solute, and usually the implicit solvation is fine for this kind of calculations.
All right, thank you so much. I believe we're running out of time. We would have some more questions in the chat. And please, if you'd like to answer the questions after in the chat for the people who are asking, I believe it would be interesting for the audience. But thank you so much for your presence here, for your availability. There was a very, very good talk. Thank you, Dia. Well, up next, we have the Master of Sciences, Letícia Maia Prates, from the Universidade do Estado do Rio de Janeiro. She will give us a lecture entitled Computational Study of Metal Support Interactions and Palladium Clusters Supported on γ-Alumina. Thank you again for your availability, Letícia. Thank you for being here with us, sharing a part of your knowledge. Please, the screen is yours.
Olá, bom dia a todos. Quero agradecer a toda a equipe organizadora pelo convite, pela oportunidade. Esse trabalho é parte da minha tese de doutorado que eu desenvolvo na UERJ sob a coorientação do professor Maurício Cruz e sobre a coorientação do professor Valquimar da UF. E esse trabalho é intitulado Computational Study of Metal Support Interaction in Palladium Clusters Supported on γ-Alumina. I will conduct my presentation in Portuguese, but I am subtitling this presentation, and if you have any questions, I can answer at the final. Bom, desde a década de 30, pelo menos, se tem evidências de que suportes não são apenas meros espectadores em catalisadores heterogêneos, mas sim que eles atuam promovendo interações com a fase metálica capazes de promover mudanças, né, no comportamento catalítico. Essas interações são denominadas de interações metal suportes fortes, Strong Metal Support Interactions, SMSI. E existem várias causas para essas interações. Aqui nesse trabalho eu destaco a existência de um fluxo eletrônico na interface metal suporte, capaz de promover um fluxo eletrônico dentro da unidade de suporte, também dentro da unidade metal, e essa comunicação entre os átomos metálicos é denominada na literatura como interações metal-metal, MMI, e elas vão atuar de forma simultânea com as interações metal-suporte, atuando em vários fatores no catalisador, dentre elas, produzindo modificações na sua estrutura, pode controlar as etapas de crescimento, nucleação e, consequentemente, a estabilidade do catalisador, e também a sua interação com as espécies adsorvato, afetando a sua atividade e seletividade. Então, entender como esses processos acontecem de forma simultânea é fundamental para o design racional de catalisadores heterogêneos mais eficientes. Bom, esse trabalho tem o foco em catalisadores de paládio suportado em γ-Alumina, amplamente empregados na catálise automotiva e em reações na indústria petroquímica. A γ-Alumina, embora seja um suporte amplamente utilizado, ainda se tem grandes discussões na literatura acerca de qual a sua real estrutura, E os principais pontos de discussão estão relacionados a como é a sua rede cristalina, a como os cátions alumínios estão distribuídos ao longo do bulk e da superfície. Esses cátions podem estar disponíveis em arranjos tetraédrico e octaédrico, e também quanto à forma como as hidroxilas estão distribuídas. Nesse trabalho, o foco é nesses dois primeiros pontos. O primeiro arranjo descrito na literatura para descrever a estrutura da gama-alumina se baseia num arranjo do tipo espinélio, que é o nome dado ao mineral MgL2O4, e para que se atinja a estoquiometria da gama-alumina, é necessária a introdução de vacâncias ao longo da rede. E uma das discussões é se essas vacâncias são predominantemente octaédricas ou tetraédricas, e isso levou também a se propor arranjos que não seguem a rede espinélio para gama-alumina. Entretanto, em 2011 foi publicado um trabalho que mostrou que o arranjo espinélio ele é 4,6 quilocalorias por mol, mais estável que o arranjo não espinélio, e por esse motivo ele será empregado aqui nesse trabalho. Outro ponto de discussão é quanto à superfície exposta pela gama-alumina. A literatura mostra que a terminação 1,0 é a majoritariamente exposta, e no arranjo do tipo espinélio, essa superfície ela se subdivide em dois tipos que são dispostos de forma intercalada ao longo da rede. A terminação 1,0C, que apresenta, além dos ânions oxigênio, também cátions alumínios tetraédricos, que na superfície são tricoordenados, e cátions alumínios octaédricos, que na superfície são tetracoordenados, e a terminação 1,0D, que apresenta, além dos oxigênios, alumínios com arranjo octaédrico apenas. Além disso, a literatura também aponta que quando a superfície C é exposta, ela pode sofrer um processo de reconstrução, onde os cátions alumínio tetraédrico entram na estrutura, de forma que apenas os octaédricos passam a estar disponíveis. Entretanto, trabalhos teóricos apontam que a exposição da superfície 1,0C ela pode ser interessante porque ela apresenta uma maior reatividade frente à terminação D para um grupo de moléculas. E a literatura também aponta a existência de sítios na superfície da gama-alumina de alta reatividade e de baixa coordenação, que são alumínios tri, tetra e pentacoordenados, que vão aparecer em condições de baixa hidratação e hidroxilação, e especialmente o alumínio tricoordenado tem um papel fundamental em diversos mecanismos. Então, estudar essa topografia de superfície da alumina também é bastante interessante para entender o seu comportamento catalítico. Então, com isso, o objetivo desse trabalho é propor modelos de catalisadores de paládio suportado em gama-alumina. Aqui nesse trabalho é proposto um modelo de aglomerado contendo 4 átomos de paládio suportado em alumina e entender como acontecem as interações metal-suporte e as interações metal-metal frente à exposição da superfície 1,0D e 1,0C, e isso também frente à avaliação do início de um processo de nucleação de um quinto átomo de paládio e também frente à adsorção de uma molécula NO. Para isso, a metodologia utilizada, primeiramente foi construído um modelo para expor a superfície 1,0C majoritariamente, cujos resultados foram publicados. Em seguida, decidiu-se comparar esses resultados com também a exposição da superfície 1,0D. Não foi possível utilizar exatamente o mesmo modelo devido a esse primeiro apresentar a superfície D não totalmente livre para aproximação do PD4. Então, eles têm apenas uma pequena diferença de estequiometria e ambos foram construídos com base em parâmetros experimentais de fração de raio-x. Após a produção desses modelos, foi aproximado, então, um aglomerado com geometria inicial planar, contendo 4 átomos de paládio. Durante as etapas de otimização de geometria, a alumina foi mantida fixa e os 4 átomos de paládio foram permitidos relaxar, mantendo uma simetria CS. Para a avaliação do processo de nucleação, foi, então, aproximado um quinto átomo de paládio sobre esse conjunto em diferentes modos de adsorção. Durante a otimização, a alumina foi mantida fixa e o PD5 foi permitido relaxar. E para o estudo da dissorção do NO, foi ancorada uma molécula de NO sobre esse sistema e também em diferentes modos de aproximação, e durante a otimização de geometria, o NO foi permitido relaxar. Todos esses cálculos foram feitos em nível DFT com funcional B3LIP e com software Gaussian 09. Além dessas etapas, foi também realizadas análises dos orbitais naturais de ligação e uma análise de decomposição de energia que foi feita com o software GAMES. Bom, destacando os principais resultados obtidos, primeiramente é verificado que a energia de dissorção de PD4 sobre a gama-alumina, ela é 2 vezes mais intensa sobre a terminação C do que sobre a terminação D, o que é um indicativo de que a interação metal-suporte é mais intensa nesse sistema. Além disso, essa interação ela promove uma distorção para esses arranjos de PD4 diferente. Para a forma sobre a superfície D, é gerada a forma denominada Bolt, que é caracterizada por uma distorção para cima, uma estrutura mais côncava, enquanto que sobre a face C é gerado um arranjo do tipo Butterfly, que é caracterizado por uma distorção para baixo. Para tentar mensurar a intensidade da interação metal-metal nesses sistemas, foi calculada a energia de coesão, que é a energia que vai manter esses átomos de paládio ligados entre si no aglomerado. Primeiramente, essa energia foi calculada para os sistemas isolados de paládio, e é verificado que para o arranjo inicial planar, essa energia de coesão é igual a menos 68 quilocalorias por mol. E em relação aos arranjos obtidos pela interação com a alumina, é verificado que o arranjo Bolt, obtido sobre a face D, tem uma energia de coesão superior ao arranjo Butterfly, obtido sobre a face C. Em comparação com o arranjo tetraédrico, que é a forma mais estável para PD4 isoladamente, essa energia de coesão é bem mais intensa, porque esse é o arranjo que mais privilegia ligações paládio-paládio mais curtas. Então, os arranjos provenientes da gama-alumina, eles mantêm esses átomos mais dispersos. Quando a presença da gama-alumina é considerada de fato para o cálculo dessa energia de coesão, é verificada uma inversão desse comportamento. O arranjo Bolt passa a ser menos coeso do que o arranjo Butterfly. E essa inversão de comportamento é devido a um efeito puramente eletrônico da interação metal-suporte, visto que no cálculo dessas energias de coesão, a diferença entre os dois é que apenas nesse caso, ele vai apresentar o aglomerado de alumina. Então, não há mudança de geometria de uma situação para outra. Então, o efeito é puramente eletrônico. Para avaliar como as interações metal-suporte e metal-metal atuam juntas na ligação de cada átomo de paládio ao sistema, foi calculado a sua energia de ligação, que é a energia que mantém cada átomo preso ao conjunto, e é verificado que sobre a superfície 10C, esses valores de energia de ligação são mais intensos do que sobre a superfície D. Quando essa energia de ligação é fragmentada nas suas componentes, primeiramente, a contribuição da interação com os sítios da alumina, da interação metal-metal para essa interação, é verificado que essa contribuição da MSI ela é superior para a superfície C, enquanto que quando é avaliada a contribuição da interação metal-metal para essa energia de ligação, essa contribuição metal-metal é mais intensa sobre a superfície D. Além disso, é verificado que ambos os efeitos de interação metal-suporte e interação metal-metal atuam em conjunto, provocando, atuando como um efeito sinérgico, diminuindo a energia de ligação total de cada átomo de paládio ao conjunto. O fluxo eletrônico nesses sistemas foi avaliado pelo método dos orbitais naturais de ligação e é verificado que existe uma transferência de carga preferencial no sentido paládio-alumina, e esse fluxo ele é mais intenso sobre a superfície C, provocando uma carga total positiva no PD4 e negativa sobre a gama-alumina. Então, a transferência preferencial é no sentido de retrodoação paládio-alumina. E quando essa distribuição de carga é analisada Em cada sítio é verificado que os paládios que ancoram sobre ânions oxigênios apresentam-se como os mais positivos, e essa interação paládio-oxigênio, ela foi avaliada através de um método de análise de decomposição de energia por orbital molecular localizado, que é um método que vai fragmentar a energia de interação de cada paládio com seu respectivo sítio em 5 componentes. As componentes estabilizantes, que são a eletrostática, a de polarização, que está relacionada à componente covalente, a de troca e a de dispersão, e a componente desestabilizante, que é a de repulsão. Então, é verificado que a interação paládio-oxigênio é majoritariamente eletrostática, enquanto que as interações paládio-alumínio vão depender da superfície exposta pela γ-Alumina. Na superfície D, a interação paládio-alumínio octaédrico ela é 28% covalente, esse é o caráter majoritário. Já esse sítio semelhante, na superfície C, vai ter um caráter principal eletrostático. A interação paládio-alumínio tetraédrico na superfície C, ela tem um caráter majoritário covalente. Quando essas transferências eletrônicas são avaliadas quanto à sobreposição de orbitais envolvidos, é verificado que essa sobreposição é apenas efetiva nos sítios que envolvem interação paládio-alumínio octaédrico, e essas interações vão ser mais intensas também no sentido da retrodoação paládio-alumínio, novamente observada uma mudança de comportamento do alumínio octaédrico nas duas superfícies. Essa transferência eletrônica ocorre via orbital 4dz2 do paládio e 3sp com um pequeno caráter P no alumínio, e ela vai ser mais intensa, envolver mais elétrons na superfície D do que na superfície C, enquanto que a transferência paládio-alumínio tetraédrico ela vai ter um valor intermediário às duas. Então, com isso, verifica-se que o alumínio octaédrico na face D é o sítio de maior acidez de Lewis, enquanto que o alumínio tetraédrico na C vai ser o sítio mais ácido nesse caso. A avaliação do processo de nucleação do quinto átomo de paládio é observado que, quando esse átomo ancora sobre os dois sistemas, é formado um arranjo muito mais organizado para PD5 sobre a superfície D, que é um arranjo similar a uma pirâmide de base quadrada, enquanto que sobre a superfície C, esse arranjo é mais disperso, caracterizado pela formação de um tetraedro de um lado da estrutura e de um dos paládios com uma distância de ligação maior. Além disso, também é verificado que o sítio preferencial de ancoramento desses átomos de paládio vão ser os centros mais positivos de paládio, os paládios ligados ao oxigênio em ambos os sistemas. Além disso, quando é calculada a energia de nucleação desse quinto átomo, que é a energia absorvida ou liberada pela entrada desse átomo, ela vai apresentar uma energia bem menos intensa sobre a superfície C, mostrando que a nucleação é menos favorecida sobre a superfície do que sobre a terminação D. Para avaliar o efeito da interação metal-suporte nessa energia de ligação, esse cálculo também foi feito na ausência do suporte, e é verificado que o efeito da interação metal-suporte é de atenuar a energia de nucleação muito mais na superfície C, enquanto que na superfície D esse processo é ligeiramente favorecido. Quando é feita a adsorção da molécula NO sobre esses sistemas, é verificado que o NO ancora preferencialmente em modos diferentes sobre ambas as terminações. Sobre a terminação D, o sítio preferencial envolve dois centros, o modo bridge ou em ponte, enquanto que sobre a superfície C, o modo preferencial é o on-top sobre um centro. Em ambos os casos, também é visto que a posição de ancoramento preferencial são os sítios de paládio mais positivos, e ambos os valores estão em boa conformidade com o resultado experimental. Olhando agora para o possível modo bridge formado sobre a superfície C, ele é apenas o terceiro em ordem de preferência. E é interessante olhar para esse modo bridge porque é visto na literatura que o ancoramento de NO sobre mais de um centro metálico favorece a transferência eletrônica metal-molécula, o que favorece o alongamento e, consequentemente, a quebra da molécula NO. Então, esse modo, né, que envolve mais centros, ele é o preferencial apenas sobre a superfície D. Quando a gente olha novamente para esses modos de bridge, mas avaliando agora a influência da interação metal-suporte nesse processo, é verificado que a influência, no caso da terminação D, é uma influência menor e no sentido de melhorar, de aumentar essa energia de absorção em 1 quilocaloria por mol. Já sobre a terminação C, é verificado que a interação metal-suporte prejudica bastante a absorção de NO, atenuando essa energia envolvida. Quando é avaliado o fluxo de carga nesse sistema, é verificado que a transferência eletrônica no sentido de retrodoação Palladium-NO é o preferencial, o que faz com que o NO assuma uma carga negativa nesse modo de adsorção, e essa carga vai ser mais intensa sobre a superfície D, o que vai levar também a um alongamento maior da distância NO nesse sistema do que na superfície C, isso em comparação com os valores para a molécula isolada, teóricos e experimentais. E o efeito da interação metal-suporte nessa transferência eletrônica também vai ser de atenuação dessa retrodoação, porém essa atenuação também vai ser superior sobre a superfície C. Então, como principais conclusões desse trabalho, eu destaco que foi identificado um efeito de interação metal-suporte nesses sistemas, que vai ocorrer preferencialmente no sentido de retrodoação paládio-alumina, principalmente via paládio transferindo para o alumínio. Também vai acontecer uma interação metal-metal nesses sistemas que vão atuar de forma sinérgica, influenciando em alguns pontos algumas propriedades desses sistemas, incluindo na sua morfologia, o que é visto principalmente através do PD5, que apresenta um arranjo muito mais organizado sobre a superfície D do que sobre a terminação C. A interação metal-suporte, ela mostra-se como o efeito preferencial sobre a terminação C, enquanto a interação metal-metal é mais intensa na terminação D, e isso leva a duas conclusões principais. Expor a superfície C poderia ser interessante do ponto de vista da estabilização desse tipo de catalisador, porque foi visto que nessa terminação o processo de nucleação ele é desfavorecido, então isso poderia retardar a etapa de sinterização do catalisador, enquanto que a exposição da superfície D poderia ser mais interessante do ponto de vista do ancoramento da molécula NO, visto que o modo que mais favorece a quebra da molécula ele é mais favorecido sobre essa superfície. Quero agradecer a todos pela atenção, às agências de fomento, às instituições envolvidas, aos meus orientadores e a toda a equipe envolvida no evento. Muito obrigada.
Letícia, obrigado. Thank you so much for the amazing talk and beautiful presentation. Thank you so much. The explanations were very, very sound. Materials chemistry and catalysis are always hot topics. Let me see herein. Well, we have a question from Ednilson Orestes here in the chat. Hi, Letícia. Nice talk. Congrats. Is there any experimental evidence data about the PD4 or PD5 clusters conformation on the alumina surface? Did you include periodic conditions in your calculations?
Hello, Ednilson. We have some evidence about these PD4 and PD5 clusters experimentally. We are developing another work in this area where we try to grow these palladium clusters on γ-Alumina surface, and we can have more accurate information about these conformations, simulating several possibilities for this growth process. But in this work, we try to make a study more reduced, only focusing in these kind of interactions in both surfaces, but we do not try use periodical conditions in these calculations. It's only by agglomerates.
Well, thank you. I have a chained question. Actually, it is a curiosity. In the first work that you presented, did you evaluate the size, like growing the size in these molecular simulations to
The size
evaluate
of
how?
alumina.
Yeah.
Yeah, we have other models, bigger structures of γ-Alumina that we are using, including to study this process of growth, but we evaluate this to compare if the charges we obtained are reliable, so the model charges. So we compare these bigger agglomerates, and we found that it is a good our results are reliable with the bigger models.
Okay. We have more questions here coming from Lilian Weitzel Coelho Pais. The OH present been taken into account?
This model is hydroxylated. We introduce 7 hydroxyls, but there are several works in the literature that including the effect, specifically the effect of hydroxyl groups in this type of interaction. But we consider in these studied conditions of low hydroxylation to simulate. But in the literature, we have studied specifically to account these effects of hydroxylation.
All right. And she also asked, was stoichiometry maintained during all calculations?
Yes, this structure follows the stoichiometry.
Okay. Well, I don't see any more questions. I believe that's it. So I'd like to acknowledge you again so much for your presentation. That was very good to have you here with us, presenting part of your work. Uh, Now, our final lecture in this morning is the Masters of Science Haroldo Candal from the Universidade Federal Fluminense, who is going to talk about his work with the collaboration of Andrew Pallock, which is an invited speaker for this afternoon. And he's going to talk thermodynamic and structural description of relative solubility of flavonoid rutin by DFT calculation and molecular dynamic simulations. So, Haroldo, thank you so much for your presence here. And now the screen is yours.
Okay, can you hear me now?
Yeah, that's perfect.
Okay, so good afternoon for everyone. First of all, I would like to thank for the invitation. And my name is Haroldo, as Professor Rodolfo said, and I'm gonna show you the recent results of the research project I've been developing during my PhD course, right? More specifically on rutin. The title of this work is Thermodynamic and Structural Description of Relative Solubility of the Flavonoid Rutin by DFT Calculations and Molecular Dynamic Simulations. This work was done with a collaboration to Professor Andrew from Miami University and Professors Luciano and Wagner from UF. Wagner is my supervisor here. Okay, rutin was the first flavonoid discovered, the first flavonoid observed experimentally, right? And it has many biological properties. Among them, we can say, for example, anti-cancer and antioxidant property. The literature makes a relation between these two properties here. Structurally, the flavonoids have a basic structure that we can find in almost all of them. It is formed by 3 rings named A, B, and C. The order of the the names is given by the order of the production in the biological media, right? So the ring A is formed first, and then the ring B, and later the ring C. What makes the rutin molecule expensive, very expensive computationally, is that right, this glycidic fraction here, formed by the glucose fraction and the remnants fraction. So we can see here a lot of sigma bonds here that can rotate almost freely, right? So the number of possibilities, the number of conformations that rutin can assume is very, very high. So it has many degrees of freedom. Sorry, okay. We have done, now about the last publication about rutin. We have done the conformational analysis of the systems involving rutin through a procedure that compares not only the energies of the conformations, which is most frequently done in the conformational analysis, but we also compared the spectroscopic properties, more specifically the chemical shifts of the hydrogens. So we can take a set of conformations, a lot of conformations, and we can compare the NMR spectrum for each of these conformations to the experimental one. The best conformation is going to be the conformations with the closest NMR spectrum to the experimental data, right? So we did this conformational analysis for rutin in DMSO solution using this comparison of the chemical shift, and among the 34 structure, we reach the structure 32 to the lowest energy and the NMR spectrum very, very close to the experimental values, right? We also did the conformational analysis of the complex, inorganic complex formed by rutin and zinc, okay? And among 25 possibility of complex, we reached the complex 3 as the best ones. So these two papers show the results with more details, right? In the middle of the papers in the literature, we found a very interesting data about the solubility of rutin. Rutin is very, very difficult to be extracted using water. So the solubility in water is very low. It was a surprise for us because we can see a lot of hydroxyl groups here. 1, 2, 3, 10 hydroxyl groups, right? And we can see, for example, the possibility of to form hydrogen bonds with water. So despite of the high number of hydroxyl groups, the solubility of rutin in water is very low, okay, close to zero. And that is the reason we investigated the solubility theoretically, right, as I'm going to show you in the next slide. So here in this figure, I show you the experimental solubility of rutin in different solvents published in this paper here. So water, methanol, ethanol, and so on. We can see that from water to methanol and to ethanol, the solubility of rutin increase. So water, that is a very polar solvent, able to do hydrogen bonds, it's not, the solubility of rutin is not favorable. So the experimental solubility show the big variation from water to the small alcohols here. Due to the importance of this property, the solubility property in the biological activity and so on, we investigated this property using quantum chemical calculations and classical simulations too. Okay, our methodology was based on the comparison, only comparison of the trends, right? That is, we compared the relative solubility of rutin in different solvents, but we didn't do the simulation of the solid state, as I'm going to explain here. So we can think, for example, in the dissolution process from the solid state to some solvent I, for example, it can be water or methanol. It doesn't matter. In two different processes. The first one is the sublimation process from solid state to the vapor phase, right, with the free energy of sublimation. And the second one is the solvation process from the vapor phase to the solvent. If we sum these two equations here, we can cancel the vapor phase, and the global equation is going to be the dissolution process from the solid state to the solvent I. Okay, the free energy of dissolution is going to be the free energy of sublimation plus the free energy of solvation. Okay, if we repeat these processes for the solvent J, here is the sublimation step with the free energy of sublimation. The second step is going to be the solvation, but in this case, in the solvent J, right? And the free energy is going to be the free energy of solvation. If we sum these two equations here, we can cancel the vapor phase again, and the global equation is going to be the dissolution process for the solvent J. The free energy of the dissolution, again, is going to be the free energy of sublimation plus the free energy of solvation. Comparing these two equations here, we can see that, let me erase, comparing these two free energies here, the second term is equal because it depends, the first one is equal because it depends only of the rutin, the pure rutin. The sublimation step is the same for the both of them, right? So if we take the first one, but in the opposite direction for the solvent to the solid state, the free energy is going to be the negative of this value. And repeating the second equation here, we can sum, canceling the solid state, and that is the reason we didn't do the simulation for the solid state. We can take the global equation from solvent I to the solvent J. That is a kind of transfer process from routine to one solvent to another one. And the free energy is going to be the free energy, the transfer free energy, okay? This is going to be the difference between the delta G of this solution. That is, canceling here the free energy of sublimation, the difference of the free energy of solvation. So we can compare the solubility, the trends in the solubility, only comparing the free energy of solvation. And we didn't need of the solid state simulation. So from the thermodynamics, the free energy in this process, this transfer process, is going to be the minus the gas constant times the temperature times the logarithm of the ratio between the concentration in the solvent J and the solvent I, right? That is the equilibrium constant, right? So this relation can be written in this form, and it is a connection between experimental property, that is the concentration, and the theoretical property that we can calculate using GFT methodology or classical simulation, right? Okay. We use the functional omega B97XG in the GFT calculations. This basis set and the bigger one, 26311 plus G2GP. We used SMG and PCM solvent models. For MG simulation, we calculated the free energy of solvation using the mute-Bennett acceptance ratio, M-bar method, right? That is based on the perturbative approach. And we change the interactions using this lambda parameter here, the van der Waals and the electrostatic lambda. It is taken account for the equations of the potential energy. Here we have the lambda of the van der Waals interactions. It is the Lennard-Jones potentials, but controlled by this lambda value here. And here we have the electrostatic energy, but controlled by the electrostatic lambda. We change from 0 to 1 gradually, right? It's a kind of change from routine to the vacuum when lambda is equal to 0 to the solvent when lambda is equal to 1, right? About the results, here we can see the blue line is the experimental solubility, but in another scale, in the logarithm scale, using the molar fractions. We can see here that the MG simulations reproduce very well the free energy of solvation, because we can see here from water to methanol, the big variation, as I've showed before, in the experimental solubility, and here in the free energy of solvation using MG simulations. This good agreement is probably due to the explicit solvent used in molecular dynamic simulations. For SMG, in the GFT calculations, the variation from water to methanol is not reached by the GFT calculations using this kind of model for the solvent interactions. When we move on to the PCM model, the agreement is better when we consider these keywords here related to the dispersion interactions, the repulsion interactions, and to the creation of the cavity. So the red line is the result for the GFT calculations considering these important keywords here. The agreement, the big variation for water to methanol is reached for this level of theory. Okay, here in this graph, we made a comparison between the transfer free energy. So we can see that the blue line, is the experimental transfer free energy, taking into account the concentration, the experimental concentration. And the green line here is related to the PCM, the GFT calculations using PCM model for the solvent effect. Again, the variation from water to methanol and ethanol is reached here from the red line. The green line, And this big variation is also reached from the MG simulations. The SMG model and the PCM model, without these important keywords here in the pink line and the red line, do not reproduce well this big variation from water to methanol. Okay. So we generated the radial and the spatial distribution functions to analyze structurally the intermolecular interactions established between the solid and the solvents, right? So in blue here, we have the spatial distribution function related to water, right? And in green, related to ethanol. We can see here that water molecules are concentrated close to the hydroxyl groups, as we expected, because hydrogen bonds are formed. And ethanol, we can also see the same interactions. But in the glycidic fraction, the ethanol molecules also interact with the CHN groups. It reveals the importance of the dispersive interactions in the solvation, in the solubilization of rutin. So probably the ethanol molecules can interact by dispersive force, and it makes difference in the solubilization process of rutin. In the radial distribution function, we can see that the peak for water is almost 1.8, and the peak for ethanol is almost 8. It reveals a high probability of finding solvent molecules around the rutin for ethanol than for water, right? So we also investigated the effect of the increase the carbon chain in the solvent molecules in the radial distribution function. So here we have the water, methanol, ethanol, 1 propanol, and 1 butanol, right? So we can see that the peak for water is very, very low, and it increased for methanol and for ethanol, which is consistent with experimental observation because the solubility in small alcohols is higher than for water, right? Okay. Here in this figure, we show the decomposition of the free energy of solvation calculated the MG simulations, right? In two factors: the van der Waals contribution and the electrostatic contribution that is given by the hydrogen bonds. Okay, so we have water, methanol, the alcohols here, acetone and heptane. For heptane, we don't have the experimental solubility. Okay, in this decomposition, we can see that for water, the experimental solubility is very, very low, okay? And the difference between the van der Waals contribution and the electrostatic contribution is very, very high. And for acetone, the difference between the van der Waals contribution and the electrostatic contribution is also very high. So the solubilization of rutin is not favorable for water and for acetone. We can see that for methanol and ethanol, the electrostatic and van der Waals contribution is very close to each other. So the solvation process seems to be favorable for the solvents that can interact with hydrogen bonds and also by dispersive interactions. So methanol and ethanol can interact by hydrogen bonds for the OH groups and by dispersion interactions using this carbon chain here. So it seems to be necessary the two kinds of interactions to solubilize rutin, the hydrogen bonds and the dispersive interactions. The reason for that is explained here in this figure. So this graph shows the same division, the contribution for each type of interactions, but in the initial stage of the perturbative approach, right? And the last one, here we have only the van der Waals interactions, and here we have the hydrogen bonds interactions. So in the first step, using only the van der Waals interactions, we can see here a very different behavior for water. It reveals the difficulty of the creation of cavity inside the water molecules, because water molecules interact using hydrogen bonds each other, and it's necessary a lot of energy to create the cavity inside the water media, right? To break the hydrogen bonds and create the cavity. And when we move to the electrostatic step here, water has a big contribution. So it's not enough to make the solubility in water favorable. So the reason for the low solubility in water seems to be related to the high energy related to the creation of the cavity inside the water media. We published this result in a paper of the Journal of Molecular Liquids, right? And if you want some details about the MG simulations, the force fields, the basis set, or something like that, you can find in this paper. I would like to thank you for the invitation. Thank you for the professors Wagner, Luciano, and Andrew for the support with this work, and the funding institutions. Thank you for your attention.
Thank you so much, Haroldo, for your presentation. That was very clear. And that was very interesting, the conclusion that you came up about the energy necessary to create the cavity is very high, since we have a lot of hydrogen bond interactions and electrostatic. That was pretty amazing. I have a question here for you. I know there is a plethora of possible methodologies that we can use to evaluate the solvation problems, as you said that you use the MD, molecular dynamics, right? Is there any rationale behind that you chose MD instead of, let's say, stochastic methods?
Oh, the reason for that is we used this work in my formation during my PhD course to learn molecular dynamic simulations only for that.
That's a very nice strategy. Since you'd like to learn, you applied to
Yeah, exactly.
That's very nice. And I have other question. I saw the routine have a glycosylation, right?
Right. Let me move to the structure of routine here.
All right. I was wondering if
here.
Yeah, I was wondering connected to the C ring, right?
Yeah.
I was wondering if you have evaluated or if would have any influence regarding the atropisomerism phenomenon. I don't know if that's present in the routine. Have you evaluated that?
No, we didn't do that. I've never heard about it before, to be honest.
Because some flavonoids classes present the atropisomerism phenomenon, which is a high barrier related to this connection between the C and O bond. And I don't know if that would affect the solubilization. Honestly, I don't see how, but I was wondering if you have a look on that.
Yeah, I actually don't know.
All right. Well, thank you. Let me see if we have more questions in the chat. No, I believe that's all. Haroldo, I'd like to thank you so much again for your talk here. That was very, very nice. Very good to see how we can address the solvation problems in organic molecules with different methodologies. That was very nice. Thank you so much for being here with us.
Okay, thank you.
People, we are closing this morning of oral lectures. I'd like to thank you all for the audience, and we will be back at 2 p.m. Brazil time. See you.